4 on Unit 11. So this is where we're starting into organic chemistry, which is the study of carbon and carbon compounds. There are very few exceptions of carbon compounds that are not considered organic compounds, such as carbon dioxide, carbon monoxide, and any carbonates. Carbon has very unique bonding properties in the fact that with 4 valence electrons, it can form 4 covalent bonds at the corners of a regular tetrahedron. Which means that it cannot just make chains with other carbon atoms. It can also make flat sheets, it can make rings, it can make three-dimensional structures. It has a huge variety of compounds that it can form, each with its own distinct properties, but also all of them have certain similarities that separates them out from what we call inorganic compounds, such as salts, for example. Some of those properties that unify organic compounds are that most of them are nonpolar molecules. They tend to be insoluble in water, as there is carbon, there is hydrogen often with it, but they're all non-metal atoms, or mostly non-metal atoms, so it's mostly a very similar electronegativity and therefore nonpolar or nearly nonpolar molecules. At the same point, that also makes them non-electrolytes. They do not dissociate into ions on a regular basis. Again, this is a general list of properties, so there are some exceptions. But mostly they are non-electrolytes. They don't have high melting points because their molecules are nonpolar. So really the top 4 properties all come back to that low or non-existing polarity in the molecules, because that causes all the properties B, C, and D. Then on the bottom, you have another set of properties that belongs together, and the really important one here is that they tend to require a high activation energy, which means they tend to react slower than inorganic compounds. Good. Then there are a bunch of new terms that you are going to use in this unit. Some of them will look familiar. You already have heard saturated and unsaturated in connection with solutions. Now we're using the same terms, but we're using them in a completely different context, and they have a different meaning. So please, whenever you read about saturation, do check out whether the question is about solutions or whether the question is about organic compounds, as the meanings are different. So in a saturated hydrocarbon, the carbon atoms have the most amount of hydrogen atoms bonded. The way that you can recognize that in a formula is that there are only single bonds between the carbon atoms. Only single bonds. If you have any other type of bonds, such as double or triple bonds between the carbon atoms, again, this is only between carbon atoms, then we call those kinds of compounds unsaturated. We also will introduce a new type of formula. So far you have seen an empirical formula, which gives you the lowest whole number ratio between the atoms involved, or ions involved, and then you saw a molecular formula which shows you the exact number and kind of atoms. And for water, that is H2O. It shows you how many hydrogen atoms there are in a water molecule and how many oxygen atoms. But if you are to show more information and show the actual arrangement of these atoms, then you're providing a structural formula, which kind of sort of a little bit like a Lewis diagram with the lines, but we're not showing any non-bonding electron pairs. So for water, the structural formula would be like this, where you see the arrangement that oxygen is in the middle, the two hydrogens are on the outside. Good. And then we have the term hydrocarbon, which the word really tells you what it is. It's a molecule containing only carbon and hydrogen, and it's hydrogen and carbon. That's all there is. Good. Then we have on the bottom of this page the start into looking at different types of hydrocarbons. So you were looking at organic compounds because they're carbon compounds. We're looking at hydrocarbons because these specific carbon compounds only contain carbon and hydrogen atoms in their molecules. And we find that we can sort these hydrocarbons into what is called homologous series. So those are compounds that are not the same, but they are similar enough that that we see that they kind of sort of should be thought of together. So we have a group of related compounds in which each member differs from the one before it by the same additional unit. So that means you have a smallest member of the group, and then you add a certain something, and that gives you the next slightly larger member of that series, and then you add that same something, and you get another slightly larger, and so on. Now, one thing that we notice about hydrocarbons, or that we can recognize in such a series of hydrocarbons, is the fact that the molecular size of molecules influences the boiling point in a way that the larger the molecule is, the higher the boiling point tends to be. Causes an increase. Let me try that again. Maybe a little better. Okay. So the first series of hydrocarbons we're going to look at more closely is the most basic one. It's saturated hydrocarbons. That means between the carbons in any compound that belongs to that series are always single bonds only. You will also find that each carbon is bonded to one or more additional carbons and possibly two hydrogens. All the bonds in these saturated hydrocarbons will end up being single bonds. You'll find information about the series, 3 different series of hydrocarbons in your reference table. To be precise, in reference table Q. And so when you look up the alkane series in that table Q, you find that the general formula is CN, with N being the number of carbon atoms, the whole number. And then the number of hydrogen can be calculated based on this number of carbons, and you find that you need to double the number of carbons and add another 2. So that's how all the alkanes have their formula. All right, so that finishes this page.